Okay, so this lecture is going to be over the magnetic vector potential. So what I'm going to do is we're going to develop a potential for the magnetic field just like we have with the electric field. Remember, for the electric field that you have E is equal to the negative of the gradient of the potential. So we developed this potential function for the electric field, and by taking a derivative of this potential, we can obtain the electric field. We're going to develop something similar for the magnetic field. And the reason that we are interested in this is, well, it's a couple of reasons. Is sometimes it's easier to calculate the magnetic field potential and then calculate the field itself. It may give some more insight into what the field looks like and so forth. And I'll show you how to develop this magnetic vector potential. So you know from Biot-Savart that the magnetic field is mu naught over 4 pi r times this integral of, that's a prime, j script r hat over script r squared d tau prime. Okay, so we already have that. This term is script r squared, or script r hat over script r squared. We can write that as the negative of the gradient of 1 over script r. So I'm going to replace this with this gradient. To get rid of the negative, I'll reverse the order of the cross product, because you know that the cross product anticommutes. So we get V of r is equal to mu naught over 4 pi. Okay, how many times do I have to say that? Anyway, it's a gradient of 1 over script r cross j d tau prime. Okay? So this is the gradient of a scalar. This is a vector. They're crossed. We have an identity for that. So I'm going to replace this integrand with a different integrand based on that identity. And the identity is this: the gradient of 1 over script r cross j. And remember that the current density depends on, it's a source, so it depends on that source term. That's equal to del cross j over script r minus 1 over script r times del cross j. Okay. Well, like we had with the Ampere's law, this is a field operator operating on a source. This is equal to 0. But this does survive. This is the source. I should have a vector here. This is a source term but this is a field term. This has arguments that depend on the field, okay? So we get that B R, or B of R, J R prime divided by script R d tau prime. Okay. So in this case, I'm going to pull this cross product out of the integral because we're integrating over the primed coordinates. This does not depend on the primed coordinates. So I can pull this out of the integral, and I'll do that. And you get it, this is equal to mu naught over 4 pi times del cross the integral of J R prime over script R d tau prime. Okay? This is what we call A. That is the magnetic vector potential, where, well, with this factor of mu naught over 4 pi. So A is equal to mu naught over 4 pi times the integral of J of R prime over script R d tau prime. Okay. So this magnetic vector potential plays the role of what we had for the electric field, which was the electric potential. So let me show you how this works. So substituting in for that magnetic vector potential, you get del cross B. So the curl of B is equal to del cross A. Okay? And all of that, of course, is equal to mu naught J. So let's look at this. Del cross A is equal to the gradient of the divergence of A minus del squared A. That's the Laplacian, okay? So you can add the gradient of any scalar. This is a scalar. This is del dot A. You can add the gradient of any scalar to this vector potential and you still get the same thing, okay? But we're going to choose that del dot A is equal to 0. We're going to choose the magnetic vector potential in such a way always that del dot A is equal to 0, so the divergence of A is equal to 0. All right? If you want to see a proof of that, you can find it in lots of places. You can find it in Griffiths. Normally, if we're doing the in-class thing, I'll go through the proof, but I'm not going to do that right now. I'll leave that up to you guys. Okay, so this gives us a nice symmetry between the electrostatics and magnetostatics, because now we have that the Laplacian of A, which is the magnetic vector potential, is equal to minus mu naught J. Note, that's three equations. This is a vector equation. You have the magnetic vector potential with the x coordinate, the y coordinate, and the z coordinate. So you have three equations to solve here. All right? And also, which we've had before, that the Laplacian of the electric potential is equal to minus rho over epsilon naught. Okay? Nice. This is nice symmetry. These are the same equation, except with this one, that magnetic vector potential depends on currents. The electric potential depends on the charge distribution. So let's go back to how we actually calculate this magnetic vector potential. In general, what I wrote down before was A is equal to the integral, let me not forget good old mu naught over 4 pi times the integral of J of r prime over script r d tau prime. Okay? For a line current, let's do a surface next. This is for volume. You're integrating over the volume. For a surface current, you replace this current density with the surface current density, and A is equal to mu naught over 4 pi times the integral of K over script R dA prime. For a line current, let me see if I can bend down here and put this down here. A is equal to mu naught I, we've got a steady current, divided by 4 pi times the integral of 1 over script R dL prime. Okay? This would be a vector inside here. You'd have a vector for this, but this is for a straight line current. Okay? So I want to calculate the magnetic vector potential for a geometry that we've seen, that we keep coming back to. We use it a lot because, it's simple. It's about as simple as it can get, and it gives you a feel for how to calculate this magnetic vector potential. So for a straight wire, okay, so here's our straight, somewhat level wire. Let's say that that's the Z direction, I. So the current is in this direction, okay? And let's take a section from negative L to L, okay? And here is the origin, and here is the point that we're interested in and let this distance equal A. Okay, so we're looking at the magnetic vector potential at this point. So like always, we're going to break it up into little segments of dl. So this would be script r. That's from the source to the point. This little section, call it dl prime. Okay, and dl prime is equal to dz z hat. Okay, because the current's in that direction, so it's a little bit of dz in the z hat direction. Script r script r is what we need. That's equal to z squared plus a squared underneath the radical. Okay, so that would be script r in terms of z. All right. So now it just amounts to calculating this integral just by symmetry. All right. By symmetry, you have a z squared, so it doesn't matter whether z is positive or negative, and you get a is 2 mu naught I over 4 pi times the integral from 0 to L. So I could have gone from negative L to L, but I'm just making it a little simpler by going from 0 to L and multiplying by 2 of dz divided by z squared plus a squared underneath the radical, and then, whoops, I already got dz. Then I needed z hat. Okay. Do the integral. Well, I did that. All right. And you get, this is equal to mu naught I over 2 pi times, let's see here. You get the ln of L plus the square root of L squared plus a squared minus ln of a z hat. Okay, that's an ln of a. All right. You know, I used to teach calculus, and at the beginning of the semester, this is limit, right? At the end of the semester, this is limit. So that's ln. That's the natural log of a. All right. And if L, so let's look at this. If L squared is much, much greater than a squared, we can do a little approximation. So say L squared is much, much greater than a squared. How much is much, much greater? Well, I mean, 10 times? All right. Meaning you have a very long wire and you're very close. Okay. So you get that in this case, for the vector potential, this is equal to mu naught I over 2 pi times the ln of 2L over a z hat. Okay? So, you know, in your spare time, see if you can get this approximation. It's not that difficult. All right. So let's see if this works. So now we have the vector potential. So if I take the curl, right, I should get the magnetic field. Let's see. I'll get rid of this. Okay. So let's recall the curl in cylindrical coordinates. Okay. So del cross A in cylindrical coordinates is equal to 1 over A d A z d phi minus d A phi over dz A hat plus dA A dz minus the derivative of AZ with respect to A phi hat, and then you have a plus 1 over A out front times d dA of A, that's little a lot of A's going on, A phi, or A sub phi, minus dA A d phi z hat. Okay? So I think in Griffiths this is an S. I used an A, but I think that's because I used the A for the vector. I mean for the distance from the wire. So I replaced that. Okay. So the only term that survives is, which one is it? Because the magnetic vector potential only depends on A. L is some constant. It depends on little a. So L is some constant, and this is the only one that survives. Okay? All the others go away. So you get that del cross A is equal to minus the derivative of AZ with respect to A phi hat. Okay? So let's do that derivative. You get minus oops. That's equal to minus mu naught I over 2 pi times dDA little a, d little a, of the ln of 2L over A phi hat. Okay, so I squeeze phi hat into the corner over there. Okay? So take this derivative, you get 1 over this, and then you have a 2L that you have to pull out front. And this equals minus mu naught I over 2 pi times A over 2L times a minus 2L over A squared. Okay, so that cancels, and these cancel, and the negative stays, that kills this negative, and you get exactly what we calculated previously for the field of a long straight wire, mu naught I over 2 pi a phi hat. And I hope I got phi in the right direction, because that means you put your thumb in the direction of z hat, and phi hat is like that. I think I got it right. Okay? So that's the idea of the magnetic vector potential. We will do some other stuff with it. We'll look at multipole expansions like we did with the electric field, and see how to do some, some approximations like we always do in physics. Hey, I hope you enjoyed it. I'll see you guys later. Bye.